All right, so today we're going to look at graphing sine and cosine. Eventually we'll look at graphing the other trig functions, but they're significantly different, so we'll just spend time on sine and cosine today, which they actually look pretty similar. Okay, so sine and cosine are what you call periodic functions. Okay. What a periodic function is it repeats. Okay. The y values start to repeat themselves over a certain interval. Okay, over, I guess you could say they repeat in the same sequence over a range of x values. Okay, let me show you an example. Okay, when you're graphing, you can do it in degrees or radians. I'm generally going to, I might use degrees, I might use radians, but if you do zoom 7, it makes it all look the same. So that's a trig zoom. Okay, so it sets the window for trig functions. Okay, and there's a graph of sine. All right, so let me let's take that. Okay, and what we're looking at, we're going to focus on one section at a time. Okay, a section that looks like that. Okay, that's called a period of the function. Okay? It's also called a cycle. Okay, we'll get to that too. Right, the idea is start, we're going to go up, we go down, we come back up, and then the y values are going to repeat again. So you're going to keep getting that pattern that repeats over the interval from here to here. Okay? Once you go through that interval, you're never going to get any new y values after that. They're just going to repeat themselves. Right, any question on that idea of it repeating? Since the graph does go on forever, we kind of got to decide how much of it we're going to sketch. I'm going to not sketch more than one period at a time. So that's, if you're sketching on paper, you'd do something like this. That would be the graph of just one period of the function. Okay, the period, okay, I've defined it right there. I already was using that word earlier with you. So the length of the interval over which the values start to repeat after that, that's called the period. And for sine and cosine, it's 2 pi radians. Okay. Anybody remember what that is in degrees? Yep. 360. So after 360 degrees, that's when your graph starts to repeat. Okay. Now we can change that 2 pi. We can stretch it, we can compress it, but we'll talk more about that later on. If you don't stretch or compress it, that's the amount of time it takes for your graph to go through all the values it's going to go through before it repeats. Okay. 2 pi radians. Okay. It's also called a cycle. That term is used a little bit more in other fields. We don't use it as much. Has anybody ever heard of that measurement? Hertz? Yeah, Hertz. So if you have like, say, alternating current, not the kind of current in your car, that's direct current, but like the current in your house. Alternating current in the United States runs at 60 hertz. And what that means is it's 60 cycles per second. Okay, it's alternating current, so that's the number of times the current alternates per second. So if you could graph it, it would basically, it would go up and down 60 times, go through 60 of those per second. Right? If that number changes, that can affect how sensitive electronic devices would run. So something like a newer TV, computers, anything with sophisticated electronics, if you didn't run it at 60 hertz, you'd probably ruin it. A light bulb, it might get brighter or dimmer a little bit. That also depends on voltage. But that's why if you go to other countries, you got to be careful when you plug stuff in, because they might not use the same electricity that system we use in the U.S. Okay? But we won't use the term cycles a lot. We'll use the term period. Right, we might have looked at this idea before. I'm not sure if we did, but there is a symmetry to sine. Okay, if you graph, say, sine of negative x, which if you put a negative on the inside, that would cause it to reflect over the y-axis. Or if you put a negative on the outside, that would cause it to reflect vertically down over the, I'm sorry, yeah, if you put it on the inside, it's the y-axis. I think that's what I said. If you put it on the outside, it's over the x-axis. Well, you won't be able to tell the difference between those two reflections. Right, so there's first one on the, they're right on top of each other. Okay, so taking the original and reflecting it over x or y comes out the same. And what that means is it's symmetric over the origin. Okay, sine is symmetric over the origin. Cosine's not symmetric over the origin, but there is symmetry. What would the negative on the inside here do? That would reflect over which axis? Your x or your y? Yeah. Anything that's inside parentheses affects what's going to happen horizontally. So when you flip horizontally, or flipping something left to right, that's like flipping it over the vertical axis. Let's take a quick look at that. So there's the original and the reflection over the y-axis. I think you can tell just by looking at the original, it's symmetrical on each side. Okay, so no symmetry over the origin, but there is symmetry over the y-axis. All right, so when we graph sine and cosine, the basic idea, you need 5 points. Okay? Sometimes when you graph a line, when you start out, they have you do 3 or 4 points in Algebra 1 to make sure you get a good line, but you really only need 2. If you're going to draw a line, you just need 2 points to make your line. If you're going to do a circle, you need 3. Okay? Any 3 points determine a circle. But for a trig function, I think 5 gives us a good amount. Okay? It kind of gives you where it starts, where it stops, gives you the middle, the highest point, and the lowest point. Okay? At least for a sine function. Remember, when you sketch it, everything here should look curved. It really shouldn't look, there shouldn't be any sharp turns in it. Okay? Everything curves nice and smooth. And if we've got 360 degrees, okay, and you want to get 5 different points, well, the way you can space 5 points evenly over 360 degrees is divide by 4. Okay? So if you put a point every 90 degrees, 0, 90, 180, 270, 360. Okay? That spaces all those points nice and even. Generally, we'll do a lot of our graphs in radians. Okay, so if you decided to compress it a little bit, then these points may not all be pi over 2 radians or 90 degrees apart. They might all be 45 degrees apart. Or you may stretch it and make each point 180 degrees apart. Okay, we're not going to really look at how far apart they are. We're just going to look at how we find them. Anytime you do a transformation, you always want to start with the original table. Okay, this is your original table for sine. If you don't know where your function is starting, you can't figure out where it's going to go. All right? And these values, it's very easy to figure them out. You could graph. Let's take a look at. Let's put sine back in. And let me do it, well, let's do it in radians. If I don't change my window zoom, it's not going to look right. Okay? That is the same graph you were looking at before of sine. It's just it looks compressed because the window isn't set properly. If you go zoom 7, it'll make it look like it should. It didn't actually stretch or compress it. It just changed the window. Let's go to table. All right, so if you type in 0 for x, okay, that's where you get 0 for y. If you type in pi over 2, okay, If you remember from unit circle trig, sine was your y value. Okay? So we're trying to think when we get to 90 degrees on our unit circle, the y value is as high as it's going to go. We're up at 1. And then as we go, keep continuing, we go over to pi, that's 180. Now your y value is back at 0. If you keep going all the way around to 3 pi over 2, or 270, now your y value is as low as it's going to go. Okay, it's at -1. And then when you get all the way back around, that's 360 degrees. The height off the x-axis, it's back to 0. And then the values repeat. Okay, if you keep going past 360, go another 90 degrees to 450. Oh, now we're going to be back at 1 again. Then -1, 0, -1, 0, 1, 0, -1. And that pattern of y values will just keep continuing. Now there are values in between, like, say, 45 degrees, which would be about 0.7. But we don't need that one. If we're just trying to make a sketch, you just need the 5 points I explained earlier. 0, pi over 2 pi, 3 pi over 2, and 2 pi. And cosine has a similar table. So when we look at sine on the unit circle, that's the y value. Does anyone remember what value the cosine is on the unit circle? Yep.
The x value?
You're looking at the x position, okay, where it is on the x-axis. So when we're at 0, you're as far right as you can go. You're at 1. When you go up to pi over 2, how far are you off the y-axis? You're not. You're right on it. So your x value is 0. Okay, when you go to pi, that's as far left as you can go. So you're at -1. 3 pi over 2, you're back on the y-axis. So you're back at 0. And then 2 pi, you're back where you started. So if you wanted to break it down and looking at separate, sine is kind of looking at the y value of a point on the unit circle. Cosine is looking at the x. Any question on those tables? Okay, we'll need those for every graph we do today. All right, for each individual transformation, one column in that table I just showed you stays the same. One column is going to change. If you do multiple transformations at the same time, well, then both columns could change. But if you shift something up or down, and that's all you do, that's only going to affect the y values. Up and down would not affect x. So we'll start out just doing one transformation at a time. All right, so now we'll specifically talk about a phase shift. Okay, a phase shift is when you move the graph left or right. We called it a horizontal shift before, but it's the same idea. Phase shift is when you move left or right. Okay, so the idea, if you're looking at it in terms of like a sound frequency, which is what this program is, it would take the sound wave and it can move it left or right. Okay, any thought what that would sound like? So we play it, I'll turn it down a little bit, but if you play it, actually that's okay. If you play it just like that, that's 1,000 hertz. That's cycles per second. That's the frequency of the sound. We'll get to that a little later. But a phase shift, okay, we do a phase shift. Any thought what's going to happen if I hit play now? Yeah. Yeah. If I line it up. If I line it up just right, should be about 180, I'm still a little bit off, but if it's 180 degrees out of phase, you get this canceling effect. And it's not because we turned the volume down. I didn't touch the volume. There's a canceling. Right? And the reason we don't hear anything now is because it's coming out of one speaker. This idea would work much better if you could do it in a room where you had 2 speakers, okay? Or even not in a room, because in a room you get echo, but like outside. Okay, so the sound couldn't bounce off any walls, and you had 2 speakers. You could change the phase of one of them, and then depending on where you stood, it would sound louder or softer. So there might be a point where you stand where you can't really hear the speakers at all outside. And then as you move a little bit, it would be like going like this. Except instead of the wave moving, you'd be moving. And all of a sudden now you'd start to hear it louder if you stand here. And then you stand over here and you wouldn't hear it at all. Right? That's the effect of a phase shift. In fact, a lot of high-end cars use that idea to cancel out engine noise. So you take sound, you play another sound that cancels out the sound you started with. With frequencies, that's very easy. Okay? To cancel out a single frequency, very simple. Most noises in the real world are more complex. Just by even dropping something or making a sound, it could be 1,000 frequencies involved in that sound. So it's a little harder to cancel out that kind of noise. But they do have noise canceling headphones and that kind of stuff. Right? And part of that is based on the idea of changing the phase of a sound. Okay, if phase change looks as we would expect, it's when you add or subtract something inside the parentheses. What do you think is going to happen if you subtract? Is that going to shift it left or right? And this works exactly the same way as every transformation we've done all year. So think what happens if you subtract. Sylvia?
Right.
Yep, it's going to move it to the right. How far? Well, depends on how big A is. So if you did a plus, that's going to shift it to the left. Okay, plus is going to shift left. Now, we generally don't shift by just any amount. On this sound generator, I can shift by any amount of degrees that I want. But the common shifts that we do are 180 degrees, 45 degrees, and 90. In fact, those are probably most of the ones we'll look at. 0, 45, and 0 we won't do, but 45, 90, and 180. And it does make a big difference whether you put that number in parentheses or you put it outside. Okay, that's a phase shift. Anybody have a thought what would happen if I did that? That's not a phase shift. We're going to look at that, but...
It would just be the sign of F and you would add pi to it.
So what would that do?
It would find sine of X and move it over pi.
Can you describe the direction?
It would move it left.
Well, if it's going to go left or right, it has to be inside the parentheses. That would be a phase shift. This is a different transformation. Yeah?
Move it up pi.
Yep, that would move it up. That's a vertical shift. Okay, so whether you put the pi or whatever number it is inside or outside, it can change it from a phase shift to a vertical. Okay, so just be careful with that. All right, so how do you figure out where those 5 points, okay, remember, these 5 points, where do they shift to? Okay. Well, first of all, if you're doing a phase shift, your y's are going to stay the same. Phase shift is left and right. You're not going to do anything vertical here. So take the original table that I gave you, and you're going to copy down your y values. Okay, to find the new x's, we do what we've always done. Look at what's been added or subtracted and do the opposite. So if you see a plus pi, that really shifts it to the left, so you're going to minus pi from all the x's. So inside the parentheses, you do the opposite of what you see to each of the original x's. Okay, so we'll go through an example. So we've got sine of x minus pi over 2. Okay, first thing I need to know is my original starting values. If I don't know where I'm starting, I can't figure out where I'm going to go to. Right, so anybody tell me what are my original x's for, and make sure you look at the sine table. Actually, you could look at the cosine table. Wouldn't make a difference for x's, but yeah.
0.
Yep.
3 pi over 2 and 2 pi.
Yep. Okay, so those are my original x's. And now this is where you got to be careful. What are my y values for sine? Where do they start at? Marina?
So it's telling me to subtract pi over 2, so you would have to add pi over 2?
We will when we do that part. But let's just write the originals to start.
Okay, so the originals would be 0,
Yep.
1, 0, -1, 0.
Good. And exactly as Marina said, you see a minus pi over 2. We know that a minus shifts it to the right, so we're going to do the opposite. We're going to add pi over 2 to all those values. Whoop, to the x values, sorry. Because remember, we're shifting left and right. We're not shifting up and down in this one. Okay, the worst thing about a phase shift is sometimes we have to find a common denominator because we have fractions to add. But that's really the worst thing that happens. And we have to write those down. Okay, don't just leave it like that. That's good. That is what you have to do. But now we got to simplify it. Okay, so let's write our final table. I won't write down the original table for every problem. I just did it for the first one so we could kind of figure it out. But if people need me to, I can. So we have 0, 1, 0, -1, 0. First one is pi over 2 plus 0. Okay, so that's going to be pi over 2. Next one is pi over 2 plus pi over 2. Orlando, what would that be?
2 pi over 2.
Yep, 2 pi divided by 2, which would reduce.
Or just pi?
Just pi, yeah. Okay, the next one we need a common denominator. It's pi over 2 plus pi over 1. What's the common denominator between 1 and 2? Yeah, go ahead. 2. So let's double the bottom, double the top. So you get pi over 2 plus 2 pi over 2. That's 3 pi over 2. The next one is pi over 2 plus 3 pi over 2. That's 4 pi divided by 2, which reduces to what? 2 pi. We always want to reduce it. I'll show you what happens if you don't reduce it. There's a nice pattern. Once you reduce it, you lose the pattern. But we do want to reduce it. Okay, and the last one, again, I need a common denominator. So let's make it double the bottom, double the top. So we have pi over 2 plus 4 pi over 2. It's 5 pi over 2. Okay, the pattern, if you didn't reduce it, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, and you could just keep going. Okay? Any question on that? So there's your table. On a test, what I usually do is I give a point for each x and each y value you get right. So you get 5 points just for copying the y values. There was nothing to even do. And then the x's, you get 5 points. And then the graph is worth 1 or 2. Okay, the graph is pretty easy. Andrew, what's the highest y value in that table? 1. And the lowest? -1. Unless you do a stretch or a shift vertically, it's always 1 and -1. And what you want to do here is label your axes using your x values. Don't label them 1, 2, 3, 4, 5, 6. That's going to make graphing awfully hard. Because now you've got to think like pi over 2. It's like 1.6 roughly. Pi is 3.1. Okay, these values are really messy. So we're going to label our axes with pi's. So pi over 2, pi. 3 pi over 2, 2 pi. 5 pi over 2. Okay, and then just graph your points. Pi over 2, 0, 1, 0, down to -1, and 0. So which way did that shift? compared to the original? It shifted about, Michael?
To the right.
Yeah, it shifted to the right. That's exactly what should have happened. The original would have been, if I can try to drag it, more like that. Would have gone from 0, ending at 2 pi. Whoops. Whoops. Might have to graph it again. Let's see. See if I can put it back. There you go. And now it goes from pi over 2 to 5 pi over 2. So we didn't stretch it or compress it. We just took the original shape and moved it. Okay, any questions on that? Okay, so we'll do one more phase shift, and then we'll move on to the next transformation. I think phase shift is one of the harder ones because you got to deal with the fractions and the pi. Some of the other transformations aren't as bad to deal with. Okay, first thing I want to do is look at it. How do I know this is a phase shift? Besides, that's the only transformation I taught you so far. What's another way that you can look at it and know?
Because you're adding something to the x inside of the parentheses.
Yeah, you're adding inside the parentheses. Okay, that makes it a phase shift. Okay, so you know what? Let's. Does anybody want to see one with cosine instead of sine? We could change it to cosine.
Yeah.
Okay, let's do the cosine instead. That's not going to change. Something here is still going to stay the same. It just makes a difference which table we copy from. All right, so we're going to copy from the cosine table. Okay, so we changed it to cosine. What stays the same for a phase shift? Your x's or your y's?
The y. No, the x. Yeah.
What stays what stays the same? What's not going to change? Think about what a phase shift does.
Your x is different.
No, x's are going to change. Remember, x's are going to change. Y's stay the same. Right? Phase shift is horizontal. It's left and right. Okay, so let's copy down our y values since they're not going to change. Kylie, can you tell me what my y values are for cosine, the originals? You can, if you have your table, you can look it up there.
Oh, is it the 0, 1?
That's for sine.
Oh.
Cosine starts off a little different.
Oh, okay. 1, 0, -1, 0, 1.
Yeah, cosine starts at the peak, comes down to 0, keeps going down to -1, back to 0, then back up to the peak. Right, now we're going to take all our x's, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Just get those from your table. And what are we going to do to each one of them?
Pi over
Do what with pi over 4? Subtract it. So we're going to minus pi over 4 from each one. Okay, we'll put our final answers inside that box. Okay, so the first one is negative pi over 4. Okay, for the next part, you're going to need a common denominator. Common denominator between 2 and 4. Sam?
4.
Yep. So we'll double the bottom, make it 4, and double the top. So you have 2 pi over 4, take away 1 pi over 4. Cassie, how much would that be?
That would be pi over 4.
Yep, pi over 4. Okay, next one, we need a common denominator again. Multiply the bottom by 4, top by 4. It's 4 pi over 4, take away 1 pi over 4, 3 pi over 4. Now rather than going through the arithmetic, let's see if we see a pattern. Because we have denominators of 4, they're all the same. -1, 1, 3. Anybody have a guess what the number in the top is going to be next? Yep. Yep. 5 pi over 4. If you're not sure, do your common denominator. You'd have 6 pi over 4. Take away 1 pi over 4. And what about my last one? Oh, Brandon? Yeah. -1, 1, 3, 5, 7. The numerator is going up by odd numbers. But again, if you don't see it, common denominator is 4 here. 8 pi over 4. Take away 1 pi over 4. There's your 7 pi over 4. Okay, and now let's make our graph. So we got negative pi over 4. Put that there. Pi over 4. Now, my next question, where is the next label going to go? Where's that next label going to? How about Brian?
On where the 3 would go?
So, can you tell me, is it right next to it?
No.
No? The next one? Yeah, it's the next one. The reason is, look at the gap between negative pi over 4 and pi over 4. That's the gap you need to maintain each time. Okay? If you don't maintain that gap, your graph isn't going to look right. Okay? So you skipped the label over the origin. All right? With pi over 4, sometimes the labeling just comes out like that. So there's 3 pi over 4, 5 pi over 4, keeping that gap the same. And I think I'm going to need one more. 7 pi over 4. Any questions why we did it that way? It'd be wrong if you placed the next label, 3 pi over 4, right there. That wouldn't be keeping the gap consistent. Okay, let's look at how the cosine looks. So you've got negative pi over 4. We're at 1, 0. -1, 0, and back to 1. Sometimes you're going to draw the graph through your numbers unless you put it above the axis, but that's fine. Now remember, this is part of a wave. Those points kind of look like a V shape, but it's really part of a wave. So it would come in like this, and we keep going. Okay, any question on that? All right, so that's how you do a phase shift. Again, probably one of the trickier ones with the arithmetic. The next two are much easier with arithmetic. Okay, a vertical shift. A vertical shift just translates in a graph up or down. And what you would see is what you'd expect. Plus is up, minus is down. So this time, your x's are going to stay the same. Okay, if you do a vertical shift, that affects the y values. And all you have to do is add or subtract whatever d was. Okay, in my problem, d was the number that was on the end. Add or subtract that to the original y values. This time, you don't do the opposite. Okay? So let's say you did sine of x. Let me put the original and then do a plus 2. All right, there's the original. And there's sine of x plus 2. So you just take each one of these y values and just push them all up 2 units. And that's it. What's nice about the vertical shift is generally you're going to shift by an integer. You're not going to shift up and down. You might do a decimal, but you're not going to usually shift by pi. That would be a very strange amount to do a vertical shift by.
That's what usually going to do.
Yeah, you're going to see problems like that. We'll do 1 up and then we'll do 1 down. Okay, what's going to stay the same, Shannon, for a vertical shift? Your x's or your y's? What's going to stay the same? Yeah, x's. Because what's a vertical shift going to do? It's going to take in, it's going to move it up or down. All right, so your y values, those are going to change because you're moving it up or down. So all the complicated numbers, all the fractions that had pi in them, they're all going to stay the same. And Taylor, what are my 5 original y values for cosine? We'll shift them up 2 after.
The 1, 0, negative 1, 0, 1.
Okay, so those are my original y's. Now we're going to add 2 to all of them. Okay, do not do the opposite. Anything that acts vertically on a function, what you see is what you do. Horizontal, that's when you do the opposite. So we're going to go plus 2, plus 2, plus 2, plus 2, plus 2. That's it. That's a vertical shift. Any question on the table? Okay, now we'll do our graph. This time, my graph is pretty much going to be contained in the first quadrant the way we draw it, so I don't need negative on the x and I don't need negative on the y this time. So make sure you label your y-axis. It's especially important to label your x-axis because I'm going to assume if you don't label it, you're going by ones. That's what we do in Algebra 1, right? We go 1, 2, 3, 4, 5. Okay, but we're not going by that. Okay, we're going every 90 degrees. So if you did it in degrees, it'd be 0, 90, 180, 270, 360. All right, so 0, 3. 2, 1, 2, and back to 3. On the homework, I'm going to give you a grid so it'll be easier for you to sketch. And that's the graph of cosine x plus 2. Okay, any questions on that? Okay, what's going to happen in this one? You don't have to graph it yet. Just tell me, how's that going to compare to sine x? Right? It's going to shift it down 3. So she said down. Down is vertical. So the y values are going to change. X's stay the same. After a while, those numbers, hopefully you'll just have them memorized. 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay, and Cassie, where do my y values start for sine?
They start at 0.
Yep, 0 and then what?
1, 0, negative 1, 0.
Okay. And we're going to take each one of those y values. And Sylvia, what am I going to do to all of these y values? Just going to minus 3. So if I take 3 away from 0, I get negative 3, negative 2, negative 3, negative 4, negative 3. That's it. That's your table. Any questions on the sketch? We skip over the sketch on this one. Okay, all it would do is take your sine function. It's going to move it down 3 units. So it's going to be in the 4th quadrant. Keep in mind, it does go on forever in each direction, left and right. But for each picture, each graph, we're only sketching one period. Okay, one period of the function. Okay, so that's your vertical shift, up and down. Okay, next thing we'll look at is our stretches. Okay, stretching vertically and horizontally. Okay, so the height of a sine or cosine wave, that's called the amplitude. And it's the height as you would measure it off that center line. So if you had a function, and let's say you had that. Okay. There's your amplitude. Would that change the amplitude if I did that?
No.
No, because you're still measuring the height off of a center line. This time it's a new center line. Okay? You get the idea. All right, so there's your height. So shifting something up and down, that doesn't affect the height. Also shifting left and right, that has no effect on the height either. So your amplitude is the height off that center line. Or it could also be how low it goes. Okay, it should be symmetrical. Okay, when you do an amplitude change, what that's going to look like, it's when you put a number in front. Okay, that number in front, I called it C. And I'll show you an example. Let's say you had cosine x and cosine, well, not like that, 2 cosine x. Okay, what this is going to do is, the 2 is going to make it twice as tall. It doubled the amplitude. Okay, any thought what that would do to a sound? If you doubled the amplitude of it? Yeah?
Make it more high-pitched?
Okay, so it could change pitch. What else could it change? Yep.
It's going to be louder.
You could change volume. In this case, it does change volume. Okay, so if you take, let's play a sound. Okay, on that speaker, it's harder to hear, but it does get louder. And then if you drag it left, it gets softer. Until eventually you just have a horizontal line, which basically represents a volume of 0. Okay. So it does affect the volume. Now, the number in front, C, the number that C itself is can be positive or it can be negative. Okay? For example, I could have a problem like this. Well, the negative is going to do something else. We talked about that at the very beginning when we looked at sine and cosine in the symmetry. Okay, that's some kind of reflection. But it's that number right there that's changing the amplitude. Okay? So if you want to know what the amplitude is, one way to think of it is just take the absolute value of whatever's in front. That is the actual amplitude. If you want to graph it, that's when you need to also think about the negative. Because the negative causes a reflection. Okay, but the negative has no effect on the amplitude at all. Okay. All right, so if I ask you for the amplitude, make sure you always give me a positive number, because it's a height. So you'd never say the amplitude here is -4. Say it's +4. That's the amplitude. Okay, we already saw what it does. It's going to stretch or compress the graph along the y-axis. Now, these aren't to sketch, just I want you to tell me the amplitude. Okay, what would be the amplitude of 3 cosine x? Yeah.
3.
3. Yeah, that's it. How about the amplitude of 4/3 sine of x plus pi over 2 plus 6? There's a couple other things in here we learned about. We got a phase shift and a vertical shift, but don't get distracted by things that have nothing to do with amplitude.
4/3.
It's 4/3. Yep. There's other things happening, but not to the amplitude. And the last one, how about -2 sine x? Yep. 2. Now, what if I took the top one and did that? What would be the amplitude now?
3.
Still 3. What did that negative do?
They just flip it over.
Yeah, it's going to cause a reflection vertically. So it would cause it to flip over the x-axis. So if I ask you for finding the amplitude, that's all you got to do. All right, so we're going to stretch and compress things vertically. Which values are going to change? If you stretch something vertically, does that affect x values or y values?
It's gonna affect the
It's going to affect the
Y value.
y values, so the x's are going to stay the same. Just like they did for a vertical shift. So copy your x's down from the table. And to find your new y values, remember this is a vertical transformation. It's like the common sense one. Okay, very simple. Take your old y values and multiply them by the number in front. Notice this time I didn't put absolute value. If that number is negative, use the negative. If it's positive, use the positive. Because that negative is important. It does change the graph. Not the amplitude, but it changes the graph. Okay, first thing, when you look at that, you should probably just try to identify what transformation is it. Well, he's multiplying by a number in front. That's how you know it's a vertical stretch. Julia, which values do we not have to change?
The Y values.
So what's going to happen to this graph?
Like the X values or Y values.
Well, just describe the transformation, 3 cosine x. What's that going to do?
It's going to stretch it vertically by a factor of 2.
Yeah, it's going to stretch it vertically. So are your y values going to stay the same?
No, they're going to change.
They're going to change. So we're going to copy down the x's. Okay, your x's stay the same. Okay, no change to the x values. Okay, now you're going to take your old y values, and you're going to multiply them by 3 in this case. Okay, so we're going to triple that. Okay, Michael, can you give me my new y values if I triple all the old ones?
Three,
Yep.
0, -3, 0, 3.
Good. So there's your table. Okay, and what I'm going to do this time is instead of going by ones, I'm going to go by 3s on my vertical axis. And I'll label my x's pi over 2, pi, 3 pi over 2, 2 pi. Now plot all 5 points. 3, 0, -3, 0, back to 3. You don't have to sketch the dotted part, that's just how we keep going. Okay, any questions on your sketch? When you sketch it, pretty much every single amplitude change can look just like this. Let's say you wanted to sketch 5 cosine x. The only thing that would change would be this. You can use the exact same graph, and now it goes from 5 to -5, instead of 3 to -3. So a lot of times people will say, well, they all look the same. Yep, they do. They all look the same because you're changing how you label your scale each time. All right? And that's how I generally do it. I change my scale depending on the problem. Okay, any question on that? Okay, we'll do one more and then we'll get into our last transformation. 1/2 sine x. Okay, Andrew, what kind of transformation is that?
That is amplitude,
Yep. And how do you know?
because it has the value in front of the sign.
Perfect. You multiply by a number in front. So what stays the same here, your x's or your y's?
The exercise.
X's stays the same. Good. And Sylvia, what am I going to do to all my old y values?
I'm going to multiply by 5.
Yeah, you're going to take half of them. What you see is what you do. Bigger numbers stretch it bigger. Smaller numbers compress it, at least for vertical. Okay, so you're going to make them all half as big. So we're going to have 0, 1/2, 1, -1/2. Oops, sorry. 0, 1/2, 0, -1/2, back to 0. Let's make our sketch. I'll label my y-axis this time 1/2 and -1/2. It does get kind of annoying to have to keep labeling the x-axis, but you got to label it. So 1/2, 0, -1/2, back to 0. And that would represent a volume of the sound that's softer. Okay? The amplitude is half as high as the original. Okay? What is the amplitude in this case? Yeah.
1/2.
It is 1/2. Yep. What if I did this? What would be the amplitude now? Yeah.
1/2?
It would still be 1/2. What would happen though with the negative is it would take this graph and it would flip it this way. It would look just like that. It would be reflected. Okay, all the positives would become negative. All the negatives would become positive. Okay, and our last transformation. Okay, the one that's, I think, most interesting is the period change. So remember, our normal period is 0 to 2 pi. That's how many radians it has to go through before it repeats itself. Well, now we're going to change that. Okay, we're going to make this function either repeat faster or slower. Okay, let's see what happens. So a period change has the form y equals sine bx. If you've used the letters I've used, you already know the order to do the transformations in. If I gave you a problem with multiple, okay, you always start with your phase shift. Your second thing is your vertical shift. Horizontal stretch. Your third thing is your vertical stretch. That's why I use the letter C. And the last thing is the vertical shift. That's why I use the letter D. Okay, so it's all in order. Now, we're only going to look at examples where B is positive. If it was negative, that would cause a reflection. We're not going to do those. Just going to stick with positive values for B. What do you think a big value for B would do? Okay, we know that it's going to cause it to stretch or compress. My question is, what do you think it would do? Say B was like 50. Is that going to stretch the graph? Or is that going to compress the graph?
I think that's going to
Stretch it?
actually no, compress it.
Compress it? Yeah, it's horizontal. Anything that's the horizontal, those are the tricky ones. You got to do the opposite of what you think. So we saw that with phase shift, and it's the same with your period change. It's going to stretch or compress. Big values are going to make the graph compressed. Small values, say like 1/7, that would stretch the graph out. Okay, so if B is greater than 1, it does compress. If it's smaller than 1, it stretches. What do you think the effect on a sound would be if you do that? Stretch or compress. We saw what happens when you stretch or compress vertically. That was volume.
Does it make it a higher pitch if you compress it?
Yeah, this changes the frequency. Okay, so eventually let's go up really high. Okay, if I play that sound, you won't even hear that. That's too high to hear. It's being played. If we had a microphone or an oscilloscope, we could prove that it's actually on right now. As we start to get a little bit lower, you can definitely hear that. Most people can hear it, if you're young enough, about up into there. Can you hear that? It's okay. Some people hear it, some people don't. As you get older, you start to lose the higher pitch. So I can hear it. I can hear it up to about 16,000. That's pretty high pitch. Okay. So higher pitch sounds are they're harder to hear at low volumes. I'm sure everybody, if I played this would be very, very easy to hear. Okay, and as you get towards the lower end, it can be harder to hear at lower volumes as well. Okay, but that's a very low frequency sound. I think human hearing, if you start to get much lower than that, I can't, well, 31, you might. Yeah. I don't really have a speaker that's designed to play something that low. All right? But those are the frequencies that we can pretty much hear. Most people can hear from up around 60 hertz, even a little lower, all the way up to about 18, 19,000 is about average, and then up into here, humans start to lose it. You can't really hear that now. You're hearing something, but it's not the sound. You'd know if you were hearing it. You wouldn't like it. It'd be painful. It'd be almost painful. Okay, and there's all kinds of different effects. Okay, we can do. For example, if I play two frequencies that are slightly off, you kind of hear this like phasing in and out kind of effect. And it's not that the volume is changing. It sounds that way a little bit, but it's that the two frequencies are slightly off. Okay? The more they're off, the faster that beat you'll hear. Okay? And that's basically the idea of how frequencies on your telephone are generated. For example, if I play this frequency, and this one at the same time, that's your phone ringing. It's just two frequencies that are off from each other a little bit, so you get that kind of that phasing in and out really fast. If you change it, just change one of the frequencies by like 10 hertz, it won't sound right. Something sounds a little off. It doesn't quite sound like it should. And using those frequencies, you can control a phone. So I could make a phone call just by playing frequencies. So if we have time, maybe tomorrow, I'll show you how you can do that on your cell phone. All right, so amplitude and period. Those are two of the transformations I can ask you just to calculate something. Amplitude is finding the height. Period change is how long is the period, okay, before it starts to repeat. This is your formula. I'm going to change it to B because I think in the previous page that's the letter I used. So make sure you make that change. Okay, so B, okay, B is just the number that's in front of X. Okay, so what would be your period here? How would you first tell me what B is, and then tell me how I plug it in and find the period? Yeah, play question. T equals what?
T equals 2 pi over 2.
Yeah, in this case, that's B. Don't say the period is 2. 2 is just B. That's all that is. So now, what's the actual period here? Yep.
Pi.
Pi. So what that means is instead of going all the way to 2 pi before this graph is going to repeat, it's going to start repeating 0 to pi. So we just compressed it. It's going to repeat more often. Okay, what's B in this case? Yeah, 1/3. So dividing by 1/3 is just like multiplying by 3. We stretched this one out. Originally, it only had to go to 2 pi before it repeated. Now it's going to go all the way out 3 times as far, and then it'll start repeating. Okay. And how about this one? What's B? Yep, B is pi. So what's the period? 2. This would be a graph that if we had this, we wouldn't have to use pi on the x-axis. The period is actually just an integer, 2 radians, no pi. Cancels out. All right, so just like we've done for the other 3 transformations, figure out what's going to stay the same. Okay, that's a period change. So this time you're stretching and compressing along the x-axis. Okay, stretching or compressing along the x. So the way you figure out what are your new x values, take your old x values and divide them all by b. Each one of them. Okay, just make sure, I think I used a different letter. You can change that to b. All right, so sine 1/2 x. First, I know it's a period change because I'm multiplying by a number inside. What values are not going to be affected by the 1/2? The values, I can leave them alone. I don't have to change them. The y's. So I copy those from my original table. So now the x's are going to change. In this case, you're going to take all the old x's, and we're going to divide each one of them by what? We're going to divide them all by 1/2. So the originals are 0, pi over 2, pi, 3 pi over 2, 2 pi. Now you could think of it that way. You could divide them by 1/2. But what does that really mean? Double them. Okay, you're going to double them. So you're going to get 0, pi, 2 pi, 3 pi, 4 pi. Dividing something by 1/2 just means to double. Okay, let's graph it. So we go through the origin, 0, 0. Whoops. Fix that. Zeros. 0 on the x-axis is right there. All right, so we got 0, 0, pi 1, 2 pi 0, negative 1, and that's 4 pi, getting all squished back to 0. Okay, so in this case, we've stretched our graph out twice as long. Okay, we've made the wave twice as long as normal. Okay, normally it would have been from 0 to 2 pi. It would have been kind of in there. We stretched it out. Okay, so this one, another period change. Copy down your y values right away. Where do my y values start for cosine? Do they start at 0 or 1? Yeah. Yep. Cosine starts at 1, keeps dropping till it hits its lowest, then starts to come back up till you end where you started. And my original x values are 0, pi over 2, pi, 3 pi over 2, 2 pi. Michael, what am I going to divide each x value by this time?
Pi over 3.
I'm going to divide it by pi over 3. Now, dividing it by pi over 3 is the same as multiplying by what? 3 over pi. I'm going to think of it that way, so I don't have to think of fractions divided by fractions. So instead of dividing by pi over 3, multiply by the reciprocal, 3 over pi. Well, first one stays the same. The next one, pi over 2 times 3 over pi. Look what happens. The pi's cancel out, and I'm left with 3 divided by 2, which is 1.5. Okay, take pi times 3 over pi. What do I get here? 3? Notice the pi's, they're disappearing. Okay, the next one is 3 pi over 2 times 3 over pi. What do I get there? 4.5. And if you look at the pattern, you're just going up by 1.5 each time. 0, 1.5, 3, 4.5. Last one? 6. Okay. This time when you label your x-axis, you could go by 1s if you want. I think that would work. And you can also go by ones on the y-axis. 1, 1.5, 0. 3, negative 1. 4.5, 0. And 6, 1. It's a little off, but not bad. Any question on that one? Right, so that's your period change. We normally don't spend this much time going through each transformation, but I figured since it was a wave, that's a little new, so that's why we went a little slower through each one. So here's your order that you do them in. It's the same order we've been seeing all year. Always do your phase shift first, then period change, then vertical stretch, then vertical shift. It is possible with the vertical stretch, you could have a reflection. You can do that right after the vertical stretch if you need to. Might not always be there. And you just do each one at a time, just like I showed you. Okay, so that's your order for multiple transformations. Okay, the last part is actually something we've already done before. It's finding, basically when you graph where two things cross. Okay, so if I wanted to figure out and solve this equation, where does sine equal 0.4? What's the highest and lowest that sine goes if you don't transform it? 1 to, all right, so I know it's going to hit 0.4. If I asked you where is it going to hit 10.4, well now that'd be like asking this. Where do those cross? They don't. Okay, but 0.4 it will hit. So the way you solve it, you use your calculator. For now, take sine x, plug in 0.4, and now be careful about the window. They asked between 0 and 2 pi. So let's go from 0 up to 2 pi, and I'm in radians. If I wasn't, I could do 0 to 360, but I think they asked for radians. Y min and max, I'd go negative 2 to 2. Don't worry about anything else. How many times does it hit 0.4? Twice. Second calc, intersect. One answer is at about 2.73. That's in radians. And the other answer, calc, just get closer to that one, about 0.41. Now, if the wave kept going, how many times would that horizontal line keep hitting it? Infinite, okay? It's going to keep hitting solutions all the way down that wave forever. Later on, we'll talk about how we would write that. It's basically going to hit a new solution every period from this point and from this point. But for now, just write it the way they asked. Just those two. This one's pretty much the same idea, except now you've got a trig function on each side. Let me just type it in and show you what it looks like. So 3 cosine 0.5x. So we got a vertical stretch and a period change equal to 2 sine x. Same window as last time, 0 to 2 pi. Okay, I just barely on the edges here, so what I would probably do is go like negative 4 to 4. Okay, how many times does it look like those two graphs cross? 3. Yeah, you're going to get 1, 2, 3. Okay, so you'd have to do second calc intersect on all 3 of those, and then write your answers. Okay, any questions on that one? Okay, so there's kind of a quick introduction to how you graph trig functions. and how you can solve some basic trig equations on the calculator. This could actually be pretty hard to do by hand. So we're not going to talk about that till much later on, but for now, just use your calculator. Okay, the homework for tonight will be a worksheet. Okay, I'll make sure I try to put the worksheet in the video, and just a few extra problems on solving graphically. Page 346, 29 to 32, 36 and 39.